So let me share this then. Boom. And there we go. Okay, so this is where we left off, talking about relational database management system. So a relational database, conceptually, you have tables. A table holds the same kind of data. Each table is composed of a series of records. So records represent individual things. And each row has the same set of columns in a relational database. So for example, we have on the next slide, we have a table of people who are listed, maybe they're customers or other accounts. Each person, each record has a name, has an email, has a password, a birthday, however many other fields, and then some link to a profile picture in their in another database. Okay, so that's the idea with a relational database. You have tables for particular kinds of things. Each thing in a table is called a record or a row, and each row has the same set of columns or fields within a table. Okay, so your basic 4 database operations: insert, delete, modify, and query. So insert is adding a new record or adding a new table to your database. Deleting is obviously getting rid of one. Modifying is making a change of some kind. So for example, if you change your password, that change has to be recorded somewhere. And last, a query. A query is asking for data. Basically, you ask for some subset from a table or set of tables. For example, you might say, give me all the customers whose birthday is today so I can send them an email wishing them a happy birthday, something like that. Okay, so queries are very important for databases because typical databases read data. They pull out data from the database much more often than they make changes. So that's typically how it is. If you think of something like Facebook, for example, a photo gets written to the database exactly once, but might get viewed by hundreds or thousands or, maybe even millions of people. Okay, so queries are very important. Generally, it's extremely important for databases to process queries quickly. Now, in a relational database, queries can span across tables. For example, if you have one table that lists a set of users and another that lists a set of tables, okay, you can ask questions like, show me the complete set of photos viewed yesterday by users from Chicago. So I'm going to do this in Paint. I'm going to show you what I mean. Okay, and I'm going to go back to this. I'm going to do a new application. Let's see, there we go. We got Paint. Okay, so in Paint here, suppose I have one table of customers, right, whatever, and another table of photos, okay? So each photo has a couple fields, has the image itself, and then the original poster, right, who posted it. And the poster can correspond to individual customers. I'm going to draw a link there. Okay, so over here you might have, name or ID, you call it ID, and then email and ... and city. Okay, so in a relational database, you can use the relationships between tables to develop multi-table queries. Okay, so that's the core idea in a relational database. It's a very powerful thing. So you have different kinds of data stored in tables, but you can still make queries that integrate across them. It's difficult to do in other types of databases. Okay, so back to the slides then, because we are on a tight schedule to finish this. Okay, so the standard language for databases is called SQL, Structured Query Language. Most often pronounced SQL, although some people do say SQL. They tend to be either very old people or sometimes very young people. In any case, it's unwise to correct anyone about word pronunciation because you don't want to be that guy, right? If there's some dude in the organization who's like 75 years old and still says it SQL, just let him have that. Anyway, SQL includes command groups for all these basic things, right? Queries, data manipulation, right? Inserts or deletions or modifying data, and as well as modifying tables and columns. For example, you could add a new row not a new row, you could add a new column to a table, for example. It even includes what's called data control language for managing permissions, which users get to see which data. And all those are important. Okay, now introducing the concept of key fields. So a key field is something you have in a table to make each record uniquely identifiable. So for example, Facebook, they surely have many users with common names like John Smith. Okay, but how does Facebook differentiate them? It differentiates them by email. So that's what a key field is, a record or a column or a group of columns that's going to be unique for any record in a table, right? So if you try to log into Facebook using an email that's already in their database, they're going to say, sorry, you know, that email is already in use. You got to pick another one. So key field, never duplicated within a table, and can encompass one or more fields. I mean, obviously it has to be at least one, but you could have a set of you know, fields being a key. For example, last name, first name, and the city that somebody is in. You might choose for some reason to make that a key field. And typically it's going to be automatically checked for uniqueness before you modify a record or try to create a new one, right? Because you want to prevent an action from happening that would duplicate a key field. Now, you can have a record in one table reference a key field in another table. Then B's key within A is termed a foreign key, right? So I can go back to the example I had here a second ago. Let's go back to Paint. Okay, so in this, I'm going to say this. Let's say, well, I'll do it in blue, do it in green. Okay. Suppose ID is key for customers, right? It's a key field for customers. Then poster would be a foreign key, right? It is a key field, but not for photos. Okay, it's not something that uniquely identifies it, right? Because obviously you could have you could have a poster post multiple photos. So the image itself is going to be the unique thing, right? Or image ID, right? I just put that in. ID might be the key field there, or however you identify the images. Okay. So I'm going to end sharing them. Okay. Let's get back to the slides. I need to do that. The labs are not correlated with the lectures. I can talk a little bit more about that at 4 o'clock as well. So I'm keeping that. I'm keeping that in my head here about what I need to do. Hold on. So we're having a. I'm going to try this again. It didn't want to share PowerPoint. There we go. Let me share that. No, let's try this again. I don't know, this thing is breaking down now. All right. No, 4 p.m. will be about newsfeed. Sorry, I'm currently unable to do the application sharing for some reason. I can do the whiteboard. All right. So I'll try to go through the last few slides, but I am unable. This thing is not working. See, this is. I'm gonna try one last time. All right. Okay. Well, there we go. Yeah, they did something weird to me. There we go. Well, anyway, I guess I'll do this in Paint. So that's what I have to do. So I got to talk through this stuff. Field atomicity. So this is slide 35. So atomicity, each database field holds one element. The idea with that is it removes ambiguity from the database. So basically, let me get back to this. and share my application. Let's see if I can still do Paint. I can still do Paint. That's good. Okay. So the idea is if I have a database with a set of records, okay, like a customer, for example, I might include name, email, address, right? So let's say city and zip code. No, if I'm doing atomicity, I got to do phone number. So if I do phone numbers, okay, that's going to be a problem. Phone numbers is not atomic, right? Could include any or all of cell phone, landline, work phone, etc. Okay? So if you ask for someone's phone number, you don't know exactly which one you're going to get. Much better for atomicity would be a customer structure this way: name, email, cell phone, work phone, etc. Right? So if you want multiple phone numbers, give them each their same field. Okay. Now, relational database models typically assume that all fields are atomic. That is, anything that exists in the database exists in exactly one place. And generally, the reason why you do that, number one, so that you always get the correct answer. You can ask for what you're looking for, and you can get the right thing. The other is it facilitates uniform data formats. So if you have a phone number, right? Yeah, there's a standard way to format a single phone number, but there's not a standard way to format a long sequence of phone numbers, right? You would have to build that in yourself. So you would know if you have atomic fields, you can say, well, this phone number is going to take up exactly, 10 digits of data, and you can make your field uniform that way. Okay. Now, databases also include something called metadata. Metadata is data about the data. So for relational databases, that would include things like the names of tables, the names of columns. The database is going to work the same way regardless of what you call a table, but you still have to call it something so you can reference it within SQL. Things like the type of data that's stored in a column, where it stores integers or floating point numbers. Those are numbers with decimal points, times, dates, whatever. And the format of it. For example, if for numbers you have a maximum or a minimum value, number of decimal places, things like that. So relational databases generally practice a couple of things as far as metadata. A given column is going to hold the same data type and format for each record in the table. And when we go into Access, you'll see that. You'll see that you'll set a format for a particular column, and that will be applicable to every record in that table. Okay, but you can have some problems when data sizes are wildly divergent. For example, if you have images, some images are very small, some are very big. It's difficult to design an efficient relational database that allows for that kind of size variation. We'll talk about that a little bit in the gap. Okay. Another thing, conflicting data. So databases often have dependencies where one value inherently depends on another. For example, your current age, that'll depend on your birth date. Your city and state will depend on your zip code. So the problem that can happen, if you enter data into the system without cross-checking it, you can have conflicts. Okay, so let's go back. I'm going to share the Paint screen again. Oh, weird. Now I can see PowerPoint. Okay. Anyway. Okay. So suppose we have a table here. Again, table customer, and customer has name and city and state and zip code. Okay. It is quite possible to enter in some kind of invalid combination. Like, for example, you might say Chicago, Illinois, and give the zip code. You might hit the wrong number and do something that starts with a 7, right? So 70601. Oh no, that's invalid, right? So your database is not going to automatically check that and say, oh, that's not a valid zip code for Chicago. But if you run a query, right, if you run a query that asks for everyone in this zip code, you're going to incorrectly get this customer. If you ask for, something that includes a particular zip code in Chicago, this is supposed to be 60601, you won't get that customer, right? So the city and state are correct, but the zip code error means you're going to have your queries return erroneous results. So the way to do that, the way to fix that is basically to break it up into two tables, right? So you have one for customer, and in customer you have just name and zip code, And then you have another table for zip code, right? Table zip code. And in that one, you might list, say, 60601 and Chicago, Illinois, right? You have the city and state for every zip code. That way, as long as you know that this is correct, right, you'll at least figure out, well, if the customer's zip code is correct and we check that somehow, we can reference this table. We can use that relationship between tables. It's much less likely to make this kind of mistake then, right? As long as the zip code is correct, we at least know it's going to point to that correct location. You're not going to have this mismatch within the table. Okay. So anyway, that's one of the things that database designers look at. Now we'll go to the next slide here. I'm going to go back. I'm going to bring it back into the PowerPoint now, which I can do for some reason. Okay, so that's conflicting data. So brief recap then, relational database pros and cons. So relational databases are very efficient when data is stable. It's a good design to quickly return query results, and very importantly, to allow queries involving multiple tables. It's a great way to do that. Problem is when the data is not stable, or when the object types have wildly divergent sizes, then you get into some trouble. Okay. Another thing, it's not very flexible. So if you're doing something in Access and you want to change a new database field, you want to add in a new field, that's easy to do at small scale. But if you're at Facebook scale, you're going to have an entire system that is very carefully optimized with how the data is distributed across hardware. If you add on a new table, you're going to throw off all of that carefully calibrated system, and it's not going to work nearly as well. So it's very easy to write into a table, oh, let's make an extra field. But all the work that you have to do to adjust where your data is stored, that's going to be a huge headache. Okay. Another thing, data doesn't always neatly fit these relational schema, the design databases. For example, if you have groups of data that tend to be very large, very small, or different batches of combined data. For example, if you have a security tool that tracks data for a particular application, one application is going to have one format for its data, another application will have another format. It doesn't all pile together well in the same relational database, which requires you to have all the same fields. Last, relational databases, as long as they're on single machines. For all your data on one machine, it can be pretty fast. But if you try to do these multi-table queries, if they're branching off across multiple machines, then instead of having the database operations happen at blindingly fast electronic speeds, instead they're happening at relatively slow network or mechanical speeds. It becomes a big problem. So those are essentially the issues. Relational databases is great as long as the data structures are stable and the amount of data is not too big. Otherwise, you're going to need some other option, like, for example, a NoSQL system. Okay, so there's a bunch of different ones. These are just a few that you may have heard of, you may have not. That's okay. So basically what NoSQL systems do, in some way they relax the requirements of a relational database system. And what they tend to often give up is the ability to do something that relational databases do well, like the ability to run queries across multiple tables quickly. Okay, but they might be much better in terms of scale. For example, Facebook's Haystack system, it's split up over many pieces of hardware. And so there's a reason why you can't run a query on that to say, show me all the people from Chicago who have posted images. You can look for a particular user and the images they've posted recently, right? Because Facebook stores that together, or it's cached in RAM for easy retrieval. But you try to do some large scale query across multiple pieces of hardware, yeah, that's going to be super slow. Okay, last thing, Hadoop, again, a thing you may have heard of, but we'll talk about this closer to Google. This is fine. This is just another example of a way to retrieve certain types of data quickly. What it is, MapReduce, if you have a big job that's decomposable into a set of smaller jobs without fundamentally changing the work, Hadoop is a way that you can introduce parallelism. You can run part of the problem on each of thousands of servers and get the results back very quickly. Okay, so that's another example of a NoSQL system. Okay, so this is a good break point. I got to post these things up on Blackboard. I'm going to stop the recording and stop sharing and stop recording. If I can figure out where that is. It was here a minute ago.